it's a pleasure to be here. So indeed, I'm a professor of medical statistics at the Leiden University Medical Center, so the university hospital in Leiden. And this has been work. This is work that I have been doing with Hans van Houwelingen, who used to be the head of our department. Is now retired, and it's a paper about basically bridging the gap between two schools in dynamic prediction, one of them being landmarking and the other one being joint models. So I've got quite a number of formulas in my presentation, but like to say you should not be scared about them. I will sort of give a more broad introduction into the field of dynamic prediction. What do we try to do? And also, skip about the formulas and focus more on the general ideas behind it. So here goes. First a little bit about general prediction models. Most of the prediction models that we're using in medicine, and we're using a lot of them, they are actually important and used to guide therapy choices. So if a particular patient has a high risk of something bad happening, then we are more tempted to give more serious therapy, and otherwise we'll be lenient with the therapy. So famous examples for these prediction models are the APGAR score in infants, the Framingham risk score, which is a famous cardiovascular risk score, the Gale model, which is a model for age at onset of breast cancer, and adjuvant online, which I'm going to be using as an example, which is actually now superseded by a more modern prediction method in breast cancer, PREDICT. And that's a model that's been used to predict prognosis after the diagnosis of breast cancer. So this is a Dutch title. I'm not sure whether any Dutch-speaking persons here. It's a sort of not an error on my side, but this is a Dutch book about Komt een vrouw bij de dokter, a Dutch book about a woman with breast cancer and what happens to this woman. So, and that's my example is also about this, a woman 60 years diagnosed with breast cancer. We know a little bit about the characteristics of the tumor. It's an ER-positive tumor, grade 2. The woman has no additional health problems, and the plan is to remove the tumor with mastectomy plus radiotherapy. And so basically, this is a woman with a disease, and we call this at baseline, just at the diagnosis with breast cancer. And then the question is, what is the probability that this woman will be alive 5 years from now, 5 years from baseline? With two therapy choices, either with or without hormonal therapy and with or without chemotherapy. For that, there used to be a prediction tool online, which was called Adjuvant Online, which actually predicts 10 years probability of cancer. So basically what you do is you have a website and you fill in all these characteristics of the woman, and what you get out is a prediction of is 87% chance that this woman will be alive in 10 years if we do not give any additional therapy. And if we do give therapy, then there's a certain benefit in terms of probability to still be alive in 10 years, which is better in this case with hormonal therapy and with chemotherapy, and also with combined therapy. With combined therapy, we gain 2.7 years. 2.7 percent probability to be alive. So based on this, there was a choice that hormonal therapy and chemotherapy would be a good idea to give to this woman. And now we have a new situation. 3 years later, the woman is still the same woman, 60 years, diagnosed with breast cancer at age of 60, the same characteristics. And the surgery was now 3 years ago. After consulting Adjuvant Online, it was decided to give this therapy. So now we have a new question. The woman we are now today comes for a regular visit, and she's doing fine. And we're now 3 years after the original diagnosis, 3 years without evidence of disease. So no local recurrence, no distant metastasis. But the same question that was, it's not a therapy question anymore, but it's still a prognosis question. This woman still wants to know, does she need to worry that this disease comes back? And what is the probability that she will be alive and disease-free in 5 or 10 years from now? So it's a prognosis question that this woman has. So how do you deal with this problem, with this question? Well, I asked actually at the time some colleagues of mine in the hospital, some breast cancer surgeons, and they almost, well, I think I asked 5 of them, and they all gave the same answer. Well, we do have adjuvant online, and that adjuvant online basically says what is the probability that she will still be alive after 10 years. It's 87%. So, and that is a first temptation to use adjuvant online, but adjuvant online was not created to answer that question. It was created to answer the question, what is the probability to be alive 10 years from baseline, from the diagnosis of cancer? And we're now in a different situation. We're in a situation 3 years later where the woman is still alive and recurrence-free. So it's not a good idea to use adjuvant online. And basically, you're not using the information that has become available, namely no evidence of local recurrence, no evidence of distant metastasis. And also some covariates is a little bit more technical issue. Some of the covariates in the model may have time-varying effects, so they may be more important in the beginning of the follow-up, so maybe in the first 3 years, and later on they might not be very important anymore. So the original prediction model may not be optimal for this choice. And also, and this is maybe the most important thing, the very fact that this woman asked the question, the very fact that this woman comes to the clinic, that already changes the prognosis. The very fact of being alive changes the prognosis. And to give you some insight, hopefully, of what the effect of being alive is, let's consider 2 situations: one with a decreasing hazard and one with an increasing hazard, which will come later on. Decreasing hazard basically means, and the situation you see here, the plot of a certain hazard which is decreasing. This basically means that most of the risk of dying happens very soon after baseline. It's very soon after the diagnosis of cancer. This happens in very acute situations, for instance. Depending on the treatment, you have this a lot with transplantation, for instance, which is has a high risk of dying soon after the treatment. So this is a hazard, and then from this hazard you can basically calculate what would be the corresponding survival. This is a survival curve, and at 5 years we can read off, based on this hazard here on the left, we can read off that the 5 years probability is a little bit more than 50%. So, but now think what happens if the person is still alive 1 year after treatment, 2 years after treatment, etc., up to 5 years after treatment. So basically, what happens if let's consider maybe 5 years after treatment. What happens 5 years after treatment? Then the probability to be alive 5 further years depends on the hazard from 5 years until 10 years, and that hazard is lower than it was in the beginning. So that means a lower hazard means a higher survival probability. So what you see is that the fact of being alive increases the probability to be alive 5 further years, because that's what you see here. You see a conditional survival curve, and that's evaluated 5 years after the point where the woman is known to be alive. So if your underlying hazard is decreasing, that means that surviving a number of years increases your prognosis in terms of 5 years later, the probability to be alive increases. And the situation is reversed if you have an increasing hazard. If you have an increasing hazard, then that means that most of the risk is actually later in the follow-up. So in the first 5 years, you have to deal with a hazard which is lower than a hazard which is important if you want to say what is the probability, given that I'm still alive after 5 years, that I'll still be alive 5 years later. Or actually, I'm looking at 3 years. Okay, but that doesn't really matter. So in this case, the prognosis becomes worse because you're dealing with a time window in which the relevant hazard is higher than in the beginning. So the fact of being alive can go two ways. It can become better in case your hazard is decreasing, and it can become worse in case your hazard is increasing. So, and this is important when to consider and to keep in mind when you ask so-called dynamic prediction problems, because with the question that this woman had, I'm not at baseline, not at the situation at the start of the diagnosis of cancer, but I have a new situation. I'm alive 3 years. Maybe I have some information that should be incorporated, and now I want to know what is the probability that I'm still alive a couple of years later. So that is the idea of dynamic prediction. There's a lot of attention on prediction from start of the treatment, diagnosis, etc. That depends on the patient characteristics known at baseline, but also at later points in time and follow-up. Baseline covariates have not changed, but the event history, clinical events that should be incorporated, may have changed. And also a very common situation, which is actually the context of the remainder of my talk, is about biomarkers. Very often biomarkers are included to, for instance, PSA in prostate cancer, which is sort of measured very often. And the value of this PSA tells you a lot of your prognosis about further development of prostate cancer and your prognosis. So as a result, prognosis will have changed, and and if we want to predict further survival, we need to update our original prediction. So in the context of this woman online, we should not be using the same adjuvant online, or nowadays it's not online anymore, but we use predict. We should be using so-called dynamic prediction model. So that's the topic, the broad topic of my talk. So and I'm going to consider a special case of that, namely dynamic prediction with biomarkers. So I gave already the example of PSA, but there are many more biomarkers which are measured which are known to be associated with the prognosis of further disease development and death afterwards. So, and in this dynamic prediction with biomarkers, I think it's fair to say that there's two broad schools that are used. One of them is the school of joint models. Basically, the idea behind this, I will give a little bit more detail, is that you use a mixed model, a linear mixed model for the biomarkers, and that mixed model is then linked in a certain way to the survival outcome. And the advantage of that is a very efficient method when it's well specified, and the software available, the JM package, the JM-base package, for instance. A disadvantage is that it's computationally heavy, and it's hard to apply this method when you have, for instance, multiple biomarkers or maybe multiple sort of outcomes, like a multi-state model or whatever. Then there is the other school, which you could say is landmarking. It's more of a pragmatic approach. It's less model-based. There's typically no real model for the longitudinal markers, although in my presentation, which is trying to bridge the gap between these two models, there will be a model for the longitudinal markers, but in principle, that's not really needed. And the big advantage of this landmarking model is very easy to implement, very easy to extend to more complicated settings with very many biomarkers, etc. There's no specialized software needed. But of course, there's no such thing as a free lunch. The advantage of the joint model is the disadvantage of the landmarking model. It's less efficient. And the objective of this talk is, can we bring the two a little bit closer and bridge the gap between these two broad schools? So here, from this point onwards, I will need a little bit of notation. So we have a number of the contexts. We have a number of patients indexed by I. There are N patients. They're followed from baseline onwards, from time t equals 0 onwards, until an event which will denote with death occurs, and Ti is the time of death. And along with this, there is a continuous biomarker process, x of t of individual I is xi of t, which is actually defined as long as an individual is alive. After death, there is no real definition of this biomarker process. It's certainly not measured. And the process is observed at could be irregular times, but they can be also irregular Tij. So J is the jth, Tij is the jth observation time of subject I. And we have these measurements, of course, also with some measurement error and also with day-to-day variation. So the actual observations, there's xi evaluated at these observation times, but the actual observations are denoted as xij. And there might be other covariates present, but for the ease of sake of presentation, I will ignore them, but they can be included as well. So what do we want to do? This is our objective, it's dynamic prediction. So we want to estimate a conditional survival probability. So what is this? Ti is the time of death of this individual. We know after the break here, there's the knowledge that the person is still alive at time S. So S is a point in time, say in our example of the woman with breast cancer, 3 years after surgery, S equals 3. We know the woman is still alive, the person is alive. And we also have some history of the biomarker. Could be also other events that could be included, but we're dealing in the context of the biomarker. So we know the value of the biomarkers until that time point in time. And we want to know what is the probability that the person is still alive after with a number of, or say 5 years after the original time. So W will be 5 in that case. So W is the window, how far we want to look into the future from this prediction time S onwards. And one of the things that you could think about is, in this context, is a Cox model with a tiny dependent covariate. So we simply put this XT, the biomarker, in a Cox model, in a time dependent Cox model. And that type of Cox model is actually helpful in understanding the biology. If the beta is positive, it means that higher values of this biomarker are associated with a higher hazard and higher probability to die. And that's very helpful in understanding the biology, but there is a large but. We want to use it, something like this, in predicting the future, in obtaining this conditional survival probability. And for that purpose, this time-dependent Cox model is useless. And the reason is that in order to calculate this probability, this conditional probability depends on the hazard of death for this person between time S and time S plus W. So in the formula, we have the baseline hazard and multiplied by the value of the time dependent covariate. But we need to integrate this to say the cumulative hazard between time S, the prediction time point, and the prediction horizon. And for that, we need to know the value of the time dependent covariate. And that's precisely what we don't know. We still think of the woman 3 years after breast cancer. We would say we would need the value of certain biomarkers after this point in time. And we are not there yet. So that is basically the problem. And these two approaches that I've talked about, joint models and landmarking, are there precisely for that purpose. We need to do something to make some assumptions on how this biomarker will behave, what it will behave like between the prediction time S and the prediction horizon S plus W. So for that, a little bit more detail on the joint model. So the joint model says, okay, I'm going to make a model for how this biomarker will behave, and then I can use the knowledge of that model to use that in my prediction. So usually this is it's assumed that X follows a Gaussian process with a certain mean and a covariance function. And a very popular one is a linear mixed model with an intercept and a slope, and we have two random effects. And basically what the joint model does is to not link the hazard to the actual observed value of the time dependent covariate, but to the underlying true value of the underlying biomarker. So mu it is the actual value, and xit is the observed value, and that's a subtle but important differences. And there are more refined options. You could also say that the hazard does not depend on the actual value of the time dependent of the biomarker, but maybe on the slope. If it has increased, that could affect your hazard. And it's very important to correctly specify this model, especially the mean model, because otherwise your dynamic prediction might lead to bias. Okay, and this is the one school, the joint model. and the other school is the landmarking, and I'm calling this landmarking 1.0 because I'm going to sort of introduce a landmarking 2.0, an update of the landmarking. But the simple landmarking, originally proposed by Hans van Houwelingen in the Scandinavian Journal of Statistics, that's what this stands for, 2007. So remember, this is the objective. And the approach actually says use all the data at time S. So at the time of prediction, use all the information that you have, summarize the history of your biomarkers in a certain way, and then use that history, that summary of the history, to predict your survival. And there is no model that's important for what the value of the biomarkers will look like. The simple summary that's actually proposed in the original paper is the last observation carried forward, basically meaning at time S, we simply use the last observed value of the biomarker. And that has a disadvantage. Sometimes that last observation has been quite some while ago, and that the last observation may not be actually that important for you. And so there is a sort of, you lose some efficiency because of the age of the last observation. Okay, and actually also this aging staleness could call for some time varying effects. Okay, to address this issue, there was a work done by Michael Sweeting and colleagues in England, in the UK, which says, okay, let's fit a mixed model to the data until the landmark time point, and use the BLUP, which means the best linear unbiased predictor. Basically, which said, what does this value predict? What would be the value of the biomarker at the landmark time point? And that sort of partly deals with this staleness problem, the aging, that the last observation was some time ago. So we update what would be the most likely value to be at the landmark date, at the landmark time. Okay, so now the landmarking 2.0 approach goes actually one little step further. So here, the other two formulas that I have to explain a little bit. Sorry about that. So basically, what we want is the conditional survival probability. So we know that the person is alive at time S, and we want to know what is the probability that the person is still alive W years later, for instance. So at time S plus W. That is what we want to know. And what is this probability? Basically, this probability, if we would know the value of the time dependent covariate, xit, this would be the e to the minus the cumulative hazard between time S, the prediction time, and S plus W, the prediction horizon. So that is this thing here. The point is that we don't know the value of the time dependent covariate. So in fact, it is sort of, you can think of this as all possible future trajectories of the biomarker after the prediction time point until the prediction window, and we take the expectation of the average basically over all possible future trajectories of this biomarker. That's what this expression says. So it's a conditional expectation of this expression here, given what we know, the history, so what we have observed of the biomarkers. And this is the thing that you would have to evaluate, and they're pretty much impossible to do. Basically, you wouldn't. It's very, very difficult to evaluate this. Maybe unless you have some very simple distributions of the biomarker. So there was a paper in 1995 already, so now 30 years ago already, which says that you can, in a different context, namely measurement errors in survival analysis, that you can approximate this conditional probability basically by taking the expectation inside. We have now a different baseline hazard and a different regression coefficients, but this approximation is valid under certain conditions. So the biomarker should not be too wild, should not be too changing too quickly, and it should change regularly, and also the window should not be too far apart. But then basically this is a much easier thing to deal with, because this says here's my baseline hazard regression coefficient. And what I need now is sort of an expected value for what my biomarker will behave after the prediction time point and until the prediction horizon. So if I can evaluate this conditional expectation, then I can use that in my prediction. So there are two steps to do then. First of all, to fit a landmarking model to your data. And next step, how to use that model that you have fitted for your prediction. So to fit this landmarking model basically means that we have to evaluate this conditional expectation. And that is very easy to do, well, relatively easy to do, if we assume that xi has a normal distribution, multivariate normal distributions. It's very easy to calculate conditional expectations. So what we can do is define a working Gaussian process with a certain trend, very much like a linear mixed effects model that's also used in joint models. So that's why we're bridging the gap in a certain way. But we're doing something differently afterwards. We're using that model to estimate basically the future of the time-dependent covariate. And that yields a so-called predictable time-dependent covariate. And then we use that time-dependent covariate in a simple landmark model with the fixed effects of these time-dependent covariates. So basically what we do is, this is a complicated step maybe, but once we've done this, we can fit a time-dependent Cox model, and we rather simply get estimates of regression coefficients and a baseline hazard. So that is the model that we fit. And once we have these estimates, that means that for a future patient where we have a history of the biomarker, we can again calculate this conditional expectation for this particular patient. So we evaluate what would be the future value of the time-dependent covariates for this particular patient. And we use the estimated regression coefficients and the baseline hazard to evaluate the baseline hazard, which we need for a dynamic prediction. So this is in a nutshell how it works, but maybe, well, first of all, some properties. The similarities with the joint models is that there is an underlying model for the biomarkers. The difference with the joint models is that we don't use any integration over random effects and latent variables. So I would say the most difficult thing in the joint models is this integration of random effects. It also gives us a robust estimate of the survivor given the predictable time-dependent covariate. It may be less efficient than a joint model, but you can also look at the trajectories of the survivor before estimating the regression coefficient. So basically, you can check a little bit of your model. I will not go into too much detail what I use for our working longitudinal model, but you need a Gaussian process, a model which you can fit to your biomarkers. Okay, so let's illustrate this with some real data. So this is the CSL1 trial, which is actually used. I think it's also in the JM package. I'm not entirely sure, but it's a randomized clinical trial performed in Copenhagen to evaluate efficacy of prednisone versus placebo in patients with liver cirrhosis. And the biomarker that is used here is the so-called prothrombin index, which is an indicator of liver function. So here's the two treatments. Not really much difference. I think the difference was not significant. And here are the biomarkers over time. This is a spaghetti plot for all of the patients in the placebo group on the left and the prednisone group on the right, on how the prothrombin basically it develops over time. You see that this is a simple lowest line based on all of the observations in both of the treatment groups. So it seems to increase over time. And I think, if I remember, worse is higher is worse. Okay, so we can fit this model that I just talked about on the prednisone and placebo patients separately, with different trends and actually the same covariance parameters. So we see two different trends. It goes up a little bit more quickly for the placebo arm, although it starts at a lower number, and a little bit slower for the prednisone arm, and some values estimated for the covariance parameters. I'll skip this a little bit. So to illustrate on how these models can be used for dynamic prediction. So what we want to do is set the time S on 3 years, which basically means we are going to assume that these patients are alive, or we want to estimate a survival conditional on being alive 3 years after the start, and we take the window to be 2 years. So 3 years, it's given that the person is still alive, and we want to know what is the probability that the person is still alive 2 more years later, a window of 2 years more later. And so we use the marker values up to 3 years and not the values of the biomarkers in our prediction after 3 years. So 4 Cox models are fitted. One is the simple landmarking based on the last observed measurement, last observation carried forward. This next one is based on the BLUP, which means that we fit a linear mixed effects model until 3 years, and we basically extend the trend that this person has until the value at the prediction time. And also we are going to use landmarking 2.0, basically fit that similar model, but then also extend our prediction of what the time-dependent covariate, what the biomarker will look like after the prediction time point. There is also another one which I'm going to explain very briefly indeed later on using this so-called revival model. So basically what you can see here, this is these are the patients in the placebo and the prednisone trial. So we've been using for each of those curves. Here is a particular patient. Let's take this one. We use all of the observations before the first 3 years. So everything that has been observed for this patient up to 3 years. We fit on this whole bunch of people a linear mixed effects model. And basically we're calculating based on that model, what is the expected value of the biomarker given what we know beforehand after 3 years until 5 years, which we would need for our prediction. So in our prediction, then we fit a landmark model using these values as the time-dependent covariates, acting as if we observed them. And similarly for each of the patients in the prednisone arm. So we see a sort of a regression to the mean here. They're still rather different. Actual observations are even more different across individuals, but over time they come a little bit closer together. I want to mention revival because I think it's such an intriguing method, and it's a very interesting approach that actually can also be used to obtain a similar basically predictions of the future development of the time-dependent covariate. It's an interesting paper by Dempsey and McCulloch in 2018. I can share the PDF of the presentation. So if you want to look this paper up, so the references are at the end of my presentation. So the basic idea is to look backwards in time. So if a person dies, usually before death, you see an increase of the biomarker, for instance, or something happening with the biomarker. And you can also fit a model, a linear mixed effect model, backwards in time and use that for dynamic prediction. And that is very easy. There is an issue of how to deal with censoring, but for every one person that dies, you can basically fit a model backwards in time. And that's and based on that, you can also use that for dynamic prediction. And you can even go one step further and use such a revival model to have a different way of evaluating the time-dependent covariates. Okay, you see that if you do this based on revival, that actually the trajectories, the predicted trajectories of the biomarkers actually look quite similar to the ones based on the Gaussian processes. Okay, so here are the results of the Cox models. And this is not proof that one method is better than the others, but it does give some indication that the betas are more, so the values seem to have more information in them in terms of survival, because the regression coefficients are higher and also the resulting chi-squared are higher. But this is not really proof that they are that this landmarking 2.0 model. So this is landmarking 1.0, this is landmarking 1.5, and these two are landmarking 2.0 method. It's not yet proof that they actually predict better, but that can be shown using, in this particular data set, by the way, only by comparing the dynamic predictions. So here we also add a prediction and a comparison with the joint model. And we leave one out cross-validation one by one, leave one observation out, fit all these models, and use each of these models to predict the conditional survival probability for the person that was left out. So, and then basically we see, focusing on the prediction error, basically we see that a null model has a Brier score, a prediction error of 0.1683, and smaller is better, lower values is better because it's a prediction error. And here you see the improvement in percentage. Sometimes this is called the IPA, or the relative prediction error, the prediction error improvement. So this is the improvement in terms of prediction error. So the joint model has only got, in this case, only 2.1% increase, improvement in prediction error. The direct revival, 7%. Last observation carried forward, landmarking 1.5, about 6%. And the this is 8% and 8, a little bit more than 8% with the landmarking 2.0. I'll skip the simulation study and go right on to the discussion. So, of course, this is only one data set, and the simulation study that I skipped also gives some evidence that this landmarking 2.0 results in improved dynamic predictions. But it's, of course, uncertain in how far the results on this one data set generalize to other data sets, of course. The landmarking principle, which says that predictions should only depend on the past and nothing but the past, and also in a transparent way, I think that still firmly stands. Okay, so joint models and also this revival models seem to work actually quite nice, although it's quite complicated to get it into action, but it works a lot. Including more dimensional biomarkers, needs more thinking how to handle the correlation between the biomarker components. So that's still an issue for further research. Competing risks is actually relatively straightforward to do this. If you want to know more, at the time that I prepared this, an earlier version, this is based on an earlier version, the preprint was on the Statistics and Medicine website, but by now this paper has been published on Statistics and Medicines. And if you want to, you can look at the full code of all the analysis in our Survival LUMC GitHub page. Okay, here's the references for the landmarking earlier on, and other references also later. So thank you very much for your attention, and I'll take questions. Thanks.